Good morning everybody. Now you see, as we were dealing with biomolecules in our last class, we had dealt with macromolecules and micromolecules. Now today we will be dealing with this carbohydrate in detail. Now the word carbohydrate, carbon and hydrate, that means what? These are carbohydrates, basically these are hydrates of carbon. Now you see, that means what? It constitutes of carbon, hydrogen and oxygen, and in the ratio of 1:2:1. So 1:2:1 is the basic ratio in carbohydrates, that can be also known as hydrates of carbon. Now you see, that means whatever it is, it will have one atom of carbon, 2 of hydrogen and 1 of oxygen. So basic formula is CnH2n plus N. That means CnH2n and ON. So this is the generalized formula of carbohydrates. Now carbohydrates has been again categorized as saccharides. Why saccharides? Because the name is derived from the sweet tasting substance. That means all carbohydrate generally it tastes sweet. Now carbohydrate may have got a single unit, that is known as a monosaccharide, may have a double unit, that is known as disaccharide. Now you see, if it has got 3 to 6 units, we don't call it as trisaccharide, tetrasaccharide, we call it as oligosaccharide. That means 3 to 6 unit of carbohydrate is known as oligosaccharides. And if they have got a more complex saccharide structure, for example, if they have 100 to 1000, 100 to 1000 molecules of this carbon, then we call it as a polysaccharides, or it may be known as a carbohydrate, a very complex form. Now we will be dealing with monosaccharides, and in that monosaccharide will have, see, minimum number of carbon that has to exist will have 3 to 7. Okay, 3 to 7 carbon is there in monosaccharide. That means one saccharide unit or 1 unit of carbon will have 3 carbon compounds. Okay, so basically 3 carbon compound, it may be known as triose. It has 4 carbon, maybe tetrose, 5 carbon, that is pentose, 6 carbon, that is hexose, and 7 is heptose. Okay. Now this 3 carbon compound basically you get when this 6 carbon compound, that is glucose, when they metabolize, they get into 3 carbon compounds, and that example is glyceroaldehyde. Okay, so triose is an example. Example of triose is glyceraldehyde. Then tetrose. Tetrose means 4 carbon. So it is erythrose. OSE. See, this OSE denotes the sugar or saccharides. Okay, so tetrose, we have C4H8 and O4, that is known as erythrose. Then pentose, we know that this pentose sugar along with the phosphorus forms the main backbone of the RNA and DNA. So we have deoxyribose and ribose. Then we have hexose, that is C6H12O6. We have glucose or fructose. Okay. Now heptose, we have celloheptose. Okay, celloheptose. So this, and for your syllabus, these two, the hexose and the pentose, has to be dealt in detail. So first we will deal with the hexose and then we deal with the pentose. Okay. Now you see hexose. Basically hexose is either a glucose or a fructose, and it is C6H12O6 compound. Okay. Now generally the glucose and the fructose, see, along with the carbon chain, it has to be either an aldehyde or a keto group attached to it. Okay. So general that includes the glucose and the fructose, is a polyhydroxy compound. That means it has plenty of OH attached to it. Okay. Now, the structurally, if we see, it may be either an open chain or a ring form. Okay. Now, I will deal with the structures. Now, you see, if it is an open chain or in the ring form, we get both these formed in a solution, and you know both these are interconvertible. Interconvertible how? That means open chain can get converted into ring form and the ring form can get converted into open chain anytime. Okay. Now, this side, if you focus, you see that this portion, you see, this is a open chain glucose molecule. See, 1, 2, 3, 4, 5 and 6. We have 6 carbons here, and you see the terminal 1. That means position 1 of carbon has got the double covalent O and H. That means double covalent O and H. This is an aldehyde group, and you see here this side, one side it is OH and another, and the third one. You know, the thing is, you see the third sugar molecule, OH is this side. OH position is shifted this side, H is there, and rest 3, the OH is on this side. Okay, so this is the basic structure, and if you count it, you see you have C6, H12 and O6, and since I said it is a polyhydroxy, so you have 1, 2, 3, 4 and 5. 5 OH group to it. Now, this is an open chain. Now, when it gets into the ring structure, it is interchangeable. Now, what happens to it? You see this fifth position of the carbon and this terminal O. Okay, this forms a bond. Okay, this forms a bond and this H2O is eliminated. Okay, so when this H2O is eliminated, you see it forms a ring-like structure. That means this H, okay, and this OH. You see, this gets eliminated. Now, when this H and this OH gets eliminated, this structure forms a ring-like structure, and this C, this carbon, and one side it is OH and the other hydrogen, it is just an extension. It comes out as an extension, and here we have C, 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 C. That means we have in the ring 1, we have got 5 carbon ring, and this oxygen, see this oxygen comes up here. So, since this oxygen is here, this is the ring-like structure. So, we have a 5 carbon ring. Okay, and the bond is formed between an aldehyde and a hydroxy group. So, this type of bond is known as glycosidic bond. What a glycosidic bond is generally formed between an aldehyde and the hydroxy group with the elimination of water. So, it is a glycosidic bond. But see, here we have got 5, so we call this as a pyranose ring. That means 5 carbon ring, and here we call this as a hemiacidyl. Glycosidic bond is formed between an hydroxyl group and an aldehyde group, but here we call it as a hemiacidyl because this glycosidic bond is formed between the same carbon chain, not from any other chain. So, same carbon chain with the elimination of water, we call it as a hemiacidyl. That means same chain. Okay, so you go through it in detail, and in the next part we will be doing the pentose